Hello everyone, myself Gayathri. I'm from India and good afternoon and good morning to and all. Thanks for this opportunity and I'll be representing my team today with our work. So just a quick intro about ourselves. We completed our undergraduation in computer science at the Anna University, Chennai, India. So we are predominantly working on this deep learning and computer vision research. So yeah, today we'll be presenting our work here. So yes, let me start with a brief intro of what our research is, what exactly we proposed and its background. So basically, our model generates a new view from a given scene. So given a 2D image, our objective is to generate a 3D scene from it. So with a 2D image viewpoint, a 3D scene is synthesized from a different viewpoint. So this is basically view synthesis. It is actually the intersection of computer vision and computer graphics. It is a task of creating new views of a scene from multiple pictures of that scene. So we have proposed a novel 3D aware model that synthesizes the image with high precision. So coming on to why this research and where does it find its use, the work is basically the intersection of artificial intelligence, computer vision, and computational photography. This process of scene rendering and the generation of 3D scenes from minimal 2D images are used in a variety of vision applications like virtual reality, where immersive experiences are synthesized from given inputs, and in spatial computing, which is latest technology that's been in the news recently, and where this view synthesis is used in 3D reasoning, and also like variety of applications in video enhancement, cinematography, and in places where dynamic object detection is used. So this so primarily this cognitive understanding behind an image or a scene is necessary, and it has like a variety of applications. So coming to the existing work in this research and what are the current challenges that's being faced here. Firstly, the accurate synthesis requires a lot of input images for training the model. Like different views of a scene is required in order to build a model. However, training on such large data is not feasible, and it sometimes defies its own purpose. So that's one thing. Then even when this is handled with the help of generative networks, the range of transformation is different. Meaning to say, the amount of rotation that's being generated in the new view remains small. So that's again one challenge. And then all the current work, they revolve around just the synthetic data. Synthetic data is like just a few objects scattered everywhere, and only that kind of data is being handled currently. So what we try to do in our proposed system is overcome these limitations and come up with a powerful model. So ours will be view synthesis from a single image. So we handle this multiple view difficulty with our 3D reasoning module, which I'll be explaining. So our input is just a single view 2D image. And then ours is a generalized model that synthesizes novel scenes, and it also has a refinement network for missing regions, so that the output is more precise and the accuracy is realistic. Also, the 3D component inside our generative model allows for an interpretable manipulation of the latent features. That is, we have a 3D module where we can animate the output, like animate the trajectories from the generated view. Also upon handling the synthetic data, we worked with the real world data, like real world indoor and outdoor scenes. So this is our model, and let's quickly skim through the abstract, like what is the process. We basically take in a single view input image, and then it goes into the reasoning module where all the scene understanding happens. Scene understanding is basically we understand the context of the image. Like we extract some spatial features, the geometry, the semantics, like the context of the scene, the properties. All these learnable features are extracted in scene understanding module, and then that is given back to our scene renderer. So this is where all the learned features are rendered to give our desired output. In the meantime, we also have our query network. Query is basically giving the input of what kind of transformation is needed. Let's say there is an image that's facing straight, and if you want the new viewpoint to be generated turned towards left, so the left is our query. So we make use of ordered query, and that is given to our scene renderer, and based on that query, our new view will be transformed. So this is basically what a system is. And let me just explain what the scene understanding. So these are our primary modules. So scene understanding and 3D scene rendering are our primary modules. So since our 3D rendering is facilitated using single input image, a comprehensive understanding of the scene is vital to render the 3D view. So this modeling this 3D structure is important for capturing the relative motion of the visible objects under a view transform. For example, let's say in a restaurant picture, there is a table which is closer to the viewer and there is a door which is behind. So when we do the transformation, the table shifts more as we change the viewpoints. So that kind of relative motion, capturing those details is really essential, and that kind of information is being extracted in this module. And with our scene renderer, to represent the 3D scene structure, we project these image and their features into the latent space, which is in turn transformed using our differentiable point cloud renderer. So this is where our renderer come into place and use all the features that's being extracted in the scene understanding module. So the renderer injects these 3D into the network as the predicted 3D structure must obey these geometric principles. So that is our objective, and we try to execute them. Yeah, so this would be our SQ3DNet architecture. For flexibility, we have split into like 5 modules with initial data pre-processing. And data pre-processing is basically we extracted the frames from the videos. So our input is a 2D image, single view 2D image, but that was being extracted from the videos. So all the frame processing happened in the module 1. And then the single view, the image is fed into scene understanding. And here we have here the spatial feature networks and depth regressor network are the 2 important components. And from where we'll be extracting all the necessary features, the structural, geometric, and semantic features from these 2 networks. These are extracted here. And then all these features are mapped into our renderer, where the 3D point cloud is generated. And in the 4th module is where we'll give our input query. Input query is like turn right, turn left, turn back, come backward. So that is our query. So based on our input query, the previously generated 3D point cloud is again fed into our GQN, the generative query network, and we get our transformed new view. So the subsequent module deals with the inconsistencies that's present in the previous view. There will be a lot of missing regions as it's a new viewpoint and scene. So all those inconsistencies are being handled in module 5, so the refinement network. So this is basically our architecture, and I'll be explaining in detail each of the module and how the work flows here. So yes. Okay, so before that, I would like to mention about the dataset. So RealEstate10K and KITTI are the standard generalized datasets that are being used in view synthesis tasks. So we wanted to explore this for our baselines. So this consists of indoor and outdoor scenes. So they are like the living room scenes or a traffic scene with cars and trees, roadways. So we wanted to deal with real world objects. So this is about our dataset. Yes, so let's look into each of the modules. So first, initially the scene understanding. So we process our data and the input 2D image comes into the scene understanding module. And there we have spatial feature network and the depth regressor. So that's being handled here. So this 2 networks are responsible for mapping the raw input image into higher dimensional feature map and also a depth map. Firstly, the spatial feature network predicts the feature maps at the same resolution as the original image, so that it can extract the scene semantics that is as a higher level representation. The network actually analyzes objects in context with respect to 3D structure of the scene, its layout, the spatial and semantic relationship between objects, and high level semantic modeling happens in this network. We made use of big GAN. GANs generally they generate high resolution details. So the specific part of big GAN is used as the details can be generated using cues from all the feature equations. So that kind of precision is what we primarily looked into. So we made use of big GAN here, and in big GAN the discriminator checks the highly detailed features in the distant portions of the images, which are consistent with each other. And when we try to introduce the attention map to these feature maps, it allows the generator and also the discriminator of the big GAN to focus on different parts of the image. So pixel by pixel attention was enabled using this attention map. So this began, it is combined with the ResNet blocks. With ResNet blocks, the model progressively learn more complex features in each layer. So that is what we essentially needed. This learning the complex and intrinsic features is our aim. So we made use of big GAN to learn the higher dimensional pixel-wise features, and it helped in creating an accurate and high resolution feature maps. So yeah, so at the end of the spatial feature networks, we learn about the high-level geometrical features and we get this spatial features map. So that would be our output from the spatial features network. And then in parallel, we have our depth network. So depth network, it basically estimates the 3D structure of the input image, like the positioning of each objects in the scene. So the relative depths are essential in resizing the objects and also in order to maintain the relative positioning of the object level features. So this depth module with the help of unit, it actually takes in a 3D image and the 3 pixel image, and then predicts the depth for each pixel. So we specifically used UNet for this as it has the ability of pixel level localization. So from this we get the fine-grained details that's learned in the encoder part, and that is used to construct the depth map in the decoder part. So this was essential because preserving these sharp discontinuities at the depth edges is critical. So that was our objective. So at the end of scene understanding module, we receive both spatial features map and also depth maps. So these are fed into our renderer. So we are using a neural point cloud renderer. So what happens is these features are embedded into the point cloud. So point cloud is something, it's like a collection of three-dimensional points that is distributed in a 3D space. So as you could see in this figure below, the spatial features and depths are mapped into the point cloud, and further the point cloud is rendered using the target view, like when the query is given, based on that the transformation happens. So for the reason of using point cloud, unlike depth images, this point cloud representation, it actually preserves high quality geometric information in the 3D space. So it's found to be an efficient way. So we combine the spatial features and predicted depths to give 3D point cloud of feature vectors. Yes, so something about our renderer, it's a differential rendering. It is actually a process where which allows the gradients of 3D objects to be calculated and propagated through the images. So it helps in retaining the specific intrinsic 3D information. So here the render, it also includes a hierarchical sampling. It implements the hierarchical representation that increases rendering efficiency by uh, proportionally proportionally allocating the samples till the final rendering. So this kind of exclusive features were being used in our neural point cloud renderer, and so using this procedure, it actually allocates more samples to the region where we expect the content expect the content to be more visible. So yes, so we try to handle some of the shortcomings in the present scene renderer, like we were able to use uh, alpha over compositioning. It's a kind of accumulation technique where where we'll soften these hard rasterization decisions. So that was one of the unique feature that was found in our neural point cloud renderer, which enabled precise synthesis. And yeah, at the end here at the end of our scene renderer, we will be getting our point cloud embedded with our previous representation. And now we get into our query network. So this is where we given our query, and based on the query, the transformation happens. So make use of GQN. So this now this 3D image is mapped into a new viewpoint, and with the help of the transformation. So here GQN has both a generation network and a representation network. The representation network helps in reconstructing the contents that was previously extracted using our scene understanding module. So GQN basically has this capability of learning the probable situations and their geometrical characteristics. So that is the reason we made use of GQN here. So we made use of this, and at the end we get our newly transformed view. And also for the animated trajectories, we made use of quaternion. The rotation and translation is being guided by quaternion. So that was, so here we get our transform view. And so yes, so here what we are doing with the refinement network is basically when the viewpoint changes dramatically, there will be a large amount of missing regions. So that has to be handled, and that has to be in painted or out painted. So this the specific regions depend on both the viewpoint shift and also the image content. So to handle this, we made use of the variational autoencoder. It's a quantized variational autoencoder, and it has the ability to implement image specific custom pixel orderings. So pixel orderings is like sequentially all these pixels are identified and in painted in a way. So we used an adversarially trained refinement module to correct these local errors. So all these pixels are like those pixels that's filled initially are filled first, and then the consecutive pixels are done in a sequential way. So that is our auto-regressive refinement module. So at the end of this, we get semantically meaningful and a kind of geometrically accurate transform view. So because that was our objective, so to bring in precision and to retain all the semantic features. So yes, so our refinement module was able to perform expected results. So here, so this is our final module, and here we got our transformed new viewpoint. Yes, let me just show some of the results here. So on the left hand side is the input image, and it's an outdoor scene as you could see. And when the query is like right and backward, you could see the right hand side, the generated image. So this is our, so you could see on the top right end, this region is what is our task was. So this region was generated by our model. And also you could see the images slightly backward. And here you could see a large portion was added here. So this is turning left, and here this is these are the examples of large angle shift. And this is yet another example, and also this is the queries towards right. So let me quickly show a simple video here. So this is basically our this is what I told about generation of the 3D with animated trajectories. So this entire scene, not the entire scene, but a small part of the scene is being generated, and that is being represented in the 3D scene render. So yes, so here you could see on the left hand side is our input image, and so upon moving the structure, we could see these are the newly generated scenes. So turning left, right, up, down. So it's kind of it resembles like a new scene. We could see, like, we could turn and see what the viewpoint is. And one more example here. So the previous one was rotation, and this is like translation. Like this is moving front and back. So like forward and backward thing. Again, left, right is done here. So on the left is our input, and we were able to synthesize this 3D from the single input image. Yes. So yes, so this is our model, and we were able to evaluate it using some of the standard metrics, and usually so during our data processing we allocated some samples for checking the similarity. Like we split it wisely into train and test data. So PSNR and SSIM, these measures, these are like it is a measure of similarity, and they are pretty good measures for consistency. And also with the help of FID, Fidget inception distance, we evaluated how well the generated images match on the distribution level. So these are like best measure for image quality. So the model is all about evaluating the quality of the scene that's generated. So there shouldn't be any inconsistencies or any missing region or anything that's not matched with the existing ones. So that was being handled here, and these are the results. Here the SQ3D-net is our proposed model, and we could see it. We could see it's comparatively better when compared to it's comparatively better with the existing baselines. So the other two are the state of the art in view synthesis with the real world images, and also we were able to achieve large angle transformation. So with the real world data, and this large angle transformation was our primary objective. So yes, so this FID value, it actually shows that our method can produce high quality and 3D consistent images. Yes, of course, with large angles. Also, our method is capable of continuing the visible scene information. So realistically, these information can be retained in a continuous flow. Uh, yes, so then we have some of the like graph. So yeah, our work is process consuming. So we needed a renderer with high performance, and since we process the batches in high resolution point clouds during the training, uh, we made there is this, like, it's process consuming, and we kind of did some ablation study based on the hours of training and the batches. And this is also like some comparative study we did with our both data set, and we find our work is pretty good when comparatively checked with the other state of the art models. So yes, so this to conclude, I would like to highlight some of the key features with our work. We kind of synthesized a rich and full world from a single image, which is still a challenging one. And requiring only a single input, it actually opens up to new experiences. But even with the single image, we were able to do a 3D awareness model. It also came up with good results and generality. I would attribute this results through to our 3D reasoning module. So the renderer along with 3D reasoning is powerful since it makes use of these intermediate representations, and it is much more flexible. So this scene understanding module was uh, was our primary component here, and it enabled semantically and geometrically precise construction of new views. So yes, so and also we introduced a query based transformation. So this is first of its kind. We encoded our queries like the right, left, all that. We encoded our queries, and we were able to achieve pretty good results from our query based network. So in future, we plan on working with high resolution images, and also still still the newly generated scene can be rendered. So there are possible occlusions and inconsistencies that's present, and we plan on handling them. Also, introducing an explainability will always be an efficient method in any of the AI work. So enhancing our work with explainability can provide a reasonable 3D rendering just with our 2D scenes. So that would open up to a lot of possibilities. And yes, so also in future, this work can be extended to give a precise input query. Like presently, we just work on the discrete one, like turning right, left, or something. In future, the angles can be precisely given as an input, and the transform view can be achieved. So that is one of the yeah. So we hope to extend this research and continue with our research interests. Yes. Thank you for your time. It's a pleasure presenting to everyone. If there is any questions, please. Thank you.